All right, so now that we know all about vectors and forces, we are going to start drawing force diagrams that need component forces. So remember, component forces are when we have a diagonal force and we want to see if how much the force pulls in the x direction and how much it pulls in the y direction, and those are the two components of that force. When we have forces at an angle, like the next couple of examples that we're going to work with in class, you need to use the components to be able to see if your force diagrams are balanced or unbalanced. Earlier, we had been doing force diagrams that were either to the right and left for forces, so we could add those forces together, or the forces were up and down, so we could add those forces together. But we're going to start seeing forces that go both right and up, or left and up, or down and right, etc. And we can't add those forces conventionally. We would have to use tip to tail. So instead, we are going to see how much the force goes right and up so we can compare that force to our other horizontal and vertical forces. So let's look at this example. We have some softball players going to camp and climbing a ropes course. And we want to draw a force diagram for the person who is hanging on the rope bridge. So from my reading, I can tell that this person is at rest, and that means that I know that everything is balanced. So the net force in the x direction, so side to side, is going to be 0. And the net force in the y direction, up and down, like the y-axis on a graph, is also going to be equal to 0 because he is not moving in any direction. He's at rest up and down and at rest side to side. So let's do our first step to drawing a force diagram just like earlier. And our first step is to draw or review the system schema. So let's start off by adding our person to the system schema. Because they are the system, they're pretty important, and since they're the system, I'm going to mark that. There we are. Also in my system schema, I always include the entire Earth or Earth's gravitational field. So I'll go and write out all the way gravitational field, which is caused by the entire planet. And then I have this person touching some ropes. I'm not sure if they are connected in the middle. It looks like they're connected, but I know that the rope going off to the left is going to pull him leftwards, and the rope going to the right is, pulling him rightwards. So I'm going to separate those two ropes. We have the left rope and the right rope as two different objects here. So now we need to draw our interactions on our system schema. Everything interacts with Earth's gravitational field. So the entire planet Earth is applying a force of gravity to everything within its field, so everything on Earth. And the person is touching the left rope, so that is going to be another interaction here. And because it's a rope, I know that's going to be tension. And the person is also touching the right rope, so that will also be tension. And it looks like the left rope and right rope are also touching each other, so let's make that tension as well. Anything with a rope is going to be tension. And nothing else is touching this person, so we're done with our system schema. So now we can move on to our force diagram. So far, you might have noticed that nothing really has changed from our straight up and down, left and right force diagrams. Nothing much has changed except for the fact that we now have to say net force twice, one for X and one for Y. But something is going to change for our force diagrams, and that is that I'm going to ask you to draw a coordinate plane. So we'll draw an imaginary x-axis and an imaginary y-axis. And we're going to put our force diagram with our dot in the center. So we are shrinking this entire picture. So the person, we are shrinking down to a dot. And we are putting this imaginary axis, both x and y directions. Okay. So now that we have that, we can start adding in our forces. Remember, I look at my system and I see which arrows are crossing that system boundary, so which ones are touching the person. And I draw an arrow for each of those interactions on my force diagram. So first, I'm going to start with force of gravity. Gravity always pulls towards the center of the earth, so that is going to be going straight downwards. And just like last time, we are going to label it with 4 letters. F for force, G for gravity, force of gravity, caused by the earth acting on the person. And notice that earth and person are the 2 objects on either side of the interaction, and that's what ended up down here on our last 2 letters. The next arrow I'm going to look at is this force of tension between the left rope and the person. I can see that the left rope is going up and to the left, and the force of tension always goes along the rope. So I'm going to draw an arrow that goes up and to the left, just like my rope does at the same angle. And I will label that the force of tension caused by the left rope acting on the person. And then I'm going to look at my last arrow, which is the other force of tension on the right rope, which I can see is going up into the right. So I'm going to draw a force of tension going up into the right. And label it with 4 letters, force of tension caused by the right rope acting on the person. And I was very intentional with how long I drew my arrows. They're not the prettiest, but I'm hoping you'll be able to see why I drew my arrows that length. I'm done with drawing arrows because I have drawn 1 arrow for every interaction on this system schema, every interaction with the person. So now my last step is to mark which forces are equal. But I can't tell which forces are equal right now because I have all of these arrows that are not parallel to each other. And we can only add up or compare the sizes of arrows that are parallel to each other, such as arrows that are left and right, or arrows that are up and down. I have 2 arrows that are not on the X and Y axis, so they're not parallel to other forces. So we have to add components so we can compare the sizes. So let's add components for the left tension. We can see that the left tension is going to the left, which is the X component, and it's going up, which is the Y component. Notice that my X component goes all the way to the left from the dot to where my tension arrow or my orange arrow stops. And the Y component goes all the way up from the X-axis to the tip of the arrow. So let's draw in another set of components for my other diagonal force. And that is my X component going to the right and my Y component going up for the right rope's tension. Looking at this force diagram, I can tell that my X direction is balanced out because these two X components are equal, and those are the only two X forces. Gravity is not pulling in the X direction, so we don't have to compare it for the X direction. So we can tell that the net force in the X direction is equal to 0 because we have Fx going left and that tension force also pulling to the right, so they cancel out. The Y direction, though, is a little trickier because we have 3 arrows to compare. We have the Y component of the left tension and the Y component of the right tension. Those are both going up. So we have the little guy for the left arrow Y component, the little one for the right arrow Y component, and then we have the force of gravity is also going along the Y-axis. So we can draw that in going down. If we add up the two Y components, we can see that they are able to cancel out that force of gravity when they're added together. So that still is going to be a balanced force. So the tension from the left rope going up and the tension from the right rope going up are enough to cancel out that downwards force of gravity, so we have a balanced force diagram. That's how you draw a force diagram with components. Notice that I did not draw congruency lines on FG because this FG is bigger than those two Y components of tension. So notice that I did not add a congruency line on there, because if I was to put numbers on this, maybe this is 1 centimeter long, and that one's 1 centimeter long. This would be 2 centimeters. Because they are not equal in size, the FG is longer than these other two. I don't mark them with congruency lines. We don't do that. All right, so that is our force diagram with components. I hope that helped.